Okay, so the next topic we're going to look at is the concept of work and energy. Um, it's going to appear to be a very long video, but the good news is once we get through this, you're going to see that the concept of work and energy is much easier to deal with than Newton's laws, because we're going to see work and energy are scalars, and that means when we do our homework problems for this, we won't, on a lot of problems, we won't even have to pick a coordinate system. And a lot of problems, we won't even have to draw forces. We'll just look at the initial and final energy states. Okay, so again, so work and energy, these are two words that you've heard before, but they have very specific definitions in physics. So going back to earlier chapter, so we said a force is anything that brings about a change. Okay, so if something is sitting in front of you and now it starts to move to the left, the thing that caused that change was a force. Energy, if you want to abbreviate the word energy, instead of writing the word energy in your notes 50 times, you can use E with a squiggle. Okay, I'm just going to use that for energy. So energy is the capacity of a body or system has to cause change. And you can even think of it in terms of a battery. You have a small battery, okay, that battery has some capacity to cause change. If you have a larger battery, let's say that you're carrying around for your phone, the bigger the battery is, the larger that battery has a capacity to cause change when you start using it. Okay, so the force is anything that brings about the change, like a push or a pull. Energy is the capacity for that force to cause change. Work is energy being transferred to a system or a body by a force, or it could be energy removed from a system by means of a force. Okay, so we'll see in certain cases where energy can be given to a system, or sometimes there can be a friction force, and that friction force can be removing energy from a moving system. Okay, now work and energy are going to be scalars. And what that means is they don't have directions, they're just numbers. Now, sometimes they can be negative, and we'll see that work is actually defined in terms of two vectors, but the resultant value is a scalar. Okay, so here I have some box, mass m, and I have a constant force. This could be like your hand, okay, and you're pulling this thing to the right, and this thing is moving to the right. Okay, so work has a very strict or very specific definition in these chapters. Okay, so what I did is I drew, this is the pulling force, that could be the tension in the string. Okay, and then it's headed to the right, so theta is my angle between the pulling force F and the direction I'm headed. So the work done by the pulling force F, okay, so the work done by that force is the component of that force along the direction it's moving multiplied by the distance through which that component acts. Okay, so if this force is 10 newtons and this distance is 3 meters, the work is not 10 times 3. Okay, it's the component of the force along the direction you're going. So it would be 10 times the cosine of that angle times that 3. Okay, so that's the strict definition of work. So by the definition of work, there's an angle between the force and the direction it's going associated with that. So in the picture, the component of the force, okay, right, that's my x component right there. I call that f sub x. So the work done by that force is the component of the force along the direction it's moving times the distance to which that force moves it through. And we'll look at the units on the next page. Okay, so looking up here, the component of the force along the direction it's going, that's f cosine, right? I just took f and I broke it up along the x direction. So the work done by that force is the component of the force along the direction it's going times the distance to which that force moves. Now all I did here is I just rearranged the f, the cosine, and the x. Okay, and now the reason that I rearranged them, we'll see on the next page, is because we'll see that the work can be written as a dot product, and we'll get to that in a second. Now, the way I wrote it here is I just rearranged the f and the x, instead of saying cosine theta, it's the cosine of the angle between the force and the distance it's headed x. So that vector x points to the right. So the work would be the force, that'd be by 10 newtons, times the distance that force moves it, which is 3 meters, times the cosine of the angle between them, which is that angle theta. Okay, now this holds when the force is constant. We'll see what happens when the force varies, but right now we're going to do when the force is constant. Let's say that's a constant 10 newtons. Okay, so we just had that the work done by this force is the same picture, is the force times the distance to which it moves times the cosine of the angle between them. Again, that's for constant forces. But in some math classes, maybe in a trig class, you look at something called a dot product, and the dot product is also called a scalar product, because there's only certain operations you can do with vectors. Okay, how can we multiply vectors? This is one way to multiply a vector. Okay, and it's called a scalar product because when we do this thing with these two vectors, we're going to get a scalar. We're going to get a number. Okay, so let's say I have two vectors. There's vector A and that's vector B. Okay, and I want to do this thing called the dot product. So this here, this is read A dot B, or it's read A dotted into B. So the definition of the dot product, definition of A dot B, is the magnitude of A times the magnitude of B times the cosine of the angle between them. And then just to make the notation easier, instead of writing my magnitude like this, I just wrote it like that. So our dot product of A and B, A dot B, and make sure that looks like a dot, okay, like a little circle. So A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between them. So in this picture, the angle between them is theta. All right. Now, what I did here, okay, is I said, okay, well, that's a magnitude, cosine of the angle, that's a number. So on the left, I have two vectors, A dot B, and on the right, I have a number. That's a scalar. So this is a way of taking two vectors, doing something to them, called a dot product. Think of it as multiplying them somehow, and I wind up with a number. Okay, so I want to look at what is the geometric interpretation of what a dot product is. Okay, so over here, okay, I wrote A dot B. Instead of writing AB cosine, right, I could write these in any order, but instead of writing AB cosine, I wrote this as B times A cosine. So I just rearranged the A, the B, and the cosine right over here. So I go here and I look up at my picture and I say, well, what is this A cosine? Well, what we've done is, let's say we had initial velocity for your projectile, okay? We've broken that up along X, and we've broken that up along Y. Okay, we resolve V0 along X, resolve V0 along Y. Well, you can also resolve a vector, let's say vector A. You can resolve vector A not along the x-axis, but you might want to resolve it along some other vector. So instead of asking what's the x component of A, you're going to ask what's the b component of A? How much b component does A have? So you're projecting A not along some x-axis. So in this picture, there's not even an x and y. You're projecting it along the b direction. So this portion right here, that length is A cosine. That's my adjacent side. So this part here, right there, that's the projection of A along B. So think of it as sort of the x component of V0. This is the b component of A. So this term here is the projection of A in the b direction. So I can take my dot product, my A dot B, instead of writing it as AB cosine, I wrote it as B times the projection of A along B. Okay, so this A cosine here, that's my projection of A along B, times the magnitude of B. So that's a geometric interpretation of the dot product. It's a projection of A along B times the magnitude of B. Now, if A and B were perpendicular, okay, so again, remember, the dot product has a cosine in it. So if these two vectors are perpendicular, if I do A dot B, it's the magnitude of A, magnitude of B, times the cosine of the angle between them. The angle between them is 90. Cosine of 90 is 0. So any two vectors that are perpendicular, their dot product is 0. So you'll use the dot product in your math classes to see whether two vectors are perpendicular. Okay. Another way of looking at this is, okay, the dot product is the projection of A along B. If I look at A and I project it along B, okay, A has no B component. It's vertical. So that's another way to see the dot product 0. Okay. Now, another place the dot product shows up is from Pythagorean theorem. Okay. So Pythagorean theorem is just a special case of the law of cosines from trig class. So from trig class, okay, that's Pythagorean theorem. Okay. This was law of cosines. Okay. And law of cosines was for something like this. If you want to find that side C, and you know two sides and the angle between them. So C squared is A squared plus B squared minus 2AB times the cosine of the angle between A and B. That'd be theta. Okay. So for the right triangle, the angle between them is 90 degrees. The angle between A and B is 90. So cosine of 90 is 0. So Pythagorean theorem is just a special case of law of cosines. Okay. So in this picture here, okay, where I have this a general triangle, it's not a right triangle, law of cosines gets me that side C. So this portion from trig class, that portion I can write as a dot product, because this AB times the cosine of the angle between them, that's just A dot B. So often you'll see law of cosines written like that in terms of a dot product. Okay, so when I write out my dot product as AB cosine, special case when you have a right triangle, angle's 90 degrees, law of cosine just reduces Pythagorean theorem. Okay, so the reason we're doing that is because way back up on the maybe second page, I had the work written like that. Okay, definition of the work done by this force was, it was the force times the distance to which that force acts times the cosine of the angle between them. And we now know that that's just a dot product. So when the force is a constant, this is for F equals a constant. When it's not constant, we'll have to integrate. But when the force is a constant, then you can write the work as F dot X. Okay, so it's the force dotted into the distance to which that force moves. So that's a scalar. So we're going to see that work, the work done by a force, defined in terms of two vectors, gives you a number. It's a scalar. Okay. Now, the units of work. Okay, so for a constant force, okay, the work done by that force is F dotted into that distance, X, okay, as a vector. Okay, so the units of force is newtons, X is meters, so a newton meter gives you a joule. So 1 newton meter is 1 joule. Now, what's a joule? Okay, so when we looked at a newton, we took an object that has a mass of 1 kilogram. Here's your liter bottle of water. You're going to apply a force, and you want to accelerate this 1 kilogram bottle. Okay, you want to change its velocity by 1 meter per second each second. So you want the acceleration to be 1 meter per second squared. And we said that if you took this numerator and converted that to miles per hour, right, our rule of thumb, so you want to speed it up by about 2.2 miles per hour each second. Okay, you want to accelerate that 1 kilogram bottle at a rate of 1 meters per second per second. The force required to do that, F is ma, so your mass is 1 kilogram, your A is 1. So the force required to do that is 1 newton. So the definition of a newton is the force required to take this 1 kilogram mass and accelerate it at a rate of 1 meters per second each second. Now, if you take that 1 newton force and you move that bottle through 1 meter of displacement, then the work done by that force is the force dotted into that distance. So it's the force of 1 newton times the distance times the cosine of the angle between them. So in the picture, force points to the right, the direction it's going points to the right, angle between those is 0 degrees, and cosine of 0 is 1. So the work done by that 1 Newton force, moving that 1 kilogram object over a distance of 1 meter, okay, gives you 1 joule of work. So that's a definition of a joule. Okay, so I took the same box, and instead of having the force at an angle, I just have, let's say, someone pulling it off to the right. Okay, so P is the pulling force off to the right. And this R is a resistive force. So I'm using R for some resistive force. Could be a friction force, but for now, think maybe there's someone else pulling back here with their hand. But this hand's pulling harder, so the box is moving to the right. So let's say I have some forces. I just stuck in some numbers. It's moving to the right. Oops, moving to the right. And let's say it moves 7 meters. And I'm going to calculate the work done on the box by all the forces. Now, there's a lot more verbiage in these chapters, so you can't just point to the picture and say, what's the work? Okay, you have to say the work done on what, by who. So I'm looking for the work done on the box by, let's say, mg. And then I want to find the work done on the box by the normal force. And I want to find the work done on the box by the pulling force, and so on. Okay, so if I want to find the work done on the box by mg, okay, the work done by mg, I take the force, mg, dot it into the distance. And if I want to find the work done by the normal force, take the normal force, dot it into the distance to which the box moves. I want to find the work done by the pushing force. I want to find the work done by the other force R. It's that force dotted into the distance through which the box moves. So let's look at the first one, A. Okay, so the work done by gravity, work done by the force mg. So it's the force, okay, times the distance to which the box moves, x, times the cosine of the angle between them. So if I look at my picture, mg points down, box is moving to the right. So the angle between those two vectors is 90 degrees. Cosine 90 is 0. So mg does no work. Okay? And you always got to remember, work has a dot product in its definition, and that means there's a cosine theta, and anytime those two vectors are perpendicular, that force does no work. If I look at the work done by the normal force, by definition, okay, I'm using this, by definition it's the force, n, times the distance to which the box moves, times the cosine of the angle between n, which points up, and the distance is moving is to the right. Cosine of 90 is 0. Whoops. Okay, so the normal force does no work. Okay, all right. That also means that if the box is just sitting there, no one's pulling on it, the box isn't going to move because mg and n don't do any work. They don't add or remove any energy by themselves. Okay, now I'm going to look at the work done by the pulling force P. Okay, so by definition, okay, part C, it's the force times the distance to which the box moves times the cosine of the angle between them. Well, P points to the right and the box is moving to the right. So the angle between them is 0 degrees. Cosine of 0 is 1. So I just get P times X. This is my 10 times 7. So work done by the pushing force, or the pulling force P is 70 joules. Okay. If I look at R, okay, for R, part D, the work done by that backwards force R, okay, it could be like an air resistance, like a drag force, okay, but it's a force that points to the left. Okay, so the work done by R is the force, R, times the distance through which the box moves, times the cosine of the angle between them. So R points to the left, box is moving to the right. So the angle between them is 180 degrees, and cosine 180 is minus 1. So R was 3, distance was 7, so I wind up with minus 21 joules. So the work done by R is negative. All right? So the way you should think of this is, here's the same picture, since the work involves a cosine. Okay, so the definition of work has a dot product which has a cosine. All right? There's that cosine. If your picture looks like this, okay, you remember from trig class, that angle theta is in the first quadrant. So cosine of theta is positive in the first quadrant. Okay. If you have an object like this, so it's moving to the right, okay, maybe there's a big pushing force to the right which wins out over this one up here. So it's moving to the right. Okay, if you want to find the work done by that force F, this angle theta, that's bigger than 90 degrees. Okay, so if you remember from trig class, if the angle's in the second quadrant, okay, any angle between 90 and 180, cosine of that angle is negative. So the work done by that force is going to be negative. So any force here in the first quadrant is going to help to move it to the right. Any force over here in the second quadrant would not help it speed up. It's trying to hinder its motion. Okay, so the work done by that type of force that points more than 90 degrees would be negative. All right, so I said here, since the work done by R is negative, okay, that force R is in a direction to prevent its motion. It's trying to hinder its motion. Okay, it's trying to remove energy from the object. So remember, work always has a dot product. You're always looking at the angle between two vectors. Okay, now I'm trying to make the connection between the new stuff and the old stuff. Okay, and this is how we're going to do that. So here's our constant force, okay, pushing on the box. And in this picture, I have it moving. So initial velocity is v0. Now it's moving faster. Okay, so in the old chapter, we'd say you apply a force, and the object accelerates. Now we're going to say you apply a force, that force does work, and the object is going to acquire some form of energy. Okay, so the work done by this force, okay, is that force, and this is a horizontal force. Okay, I'm using a horizontal force. So it's the force times the distance through which the box moves times the cosine of the angle between them. Okay, in that case, x is to the right, so the angle between the force and the vector x is 0 degrees. Cosine 0 is 1. So the work done by the force is the component of the force along the direction you're going times the distance to which that box moves. Okay, so the x component of F is just F. Okay, but from the old chapter, F is ma. So right here I have F, I put in ma. And now I see this a times x. I could have used delta x, but I just used x. That reminds me of the third equation of motion. So I wrote down equation number 3. Okay, I solved it for a delta x. Okay, so I brought the v0 over, divided by 2, and I say, ooh, here's a delta x, here's a times an x, or a times x, or a times x. So I took this quantity here and put it in for a times x. So I'd have to take all of this and multiply it by the m. Okay, so here is a delta x, the big parenthesis thing, multiplied by m, and I wind up with this. Okay, so I just took the 1/2 out. All right, so this quantity, nature's decided for some reason the quantity 1/2 mv squared shows up a lot. Not mv squared, okay, not 1/2 mv, but 1/2 mv squared. So since it's such a significant value, it's given a special name. It's called the kinetic energy. So 1/2 mv squared is the kinetic energy of the box. Now, last time we saw part of the word kinetic was in kinematics, and the root word meant motion. So the kinetic energy is the energy a body or system has due to its motion. Okay, so if 1/2 mv squared is kinetic energy, then that would be K final, and that would be K initial. So that's going to say that the work done by the force is going to change the kinetic energy. All right. Now, I want to look at the units while we're here. Okay, so kinetic energy is 1/2 mv squared. So I use an arrow, not use an equal sign. So the units of mass, kilograms, and I have speed squared. So there's meters per second times meters per second. And then I grouped those together, and I got kilogram meters per second squared, and this meter here is sitting right there, and then this part of it, that's a Newton. So I have a Newton meter. So that's a joule. So kinetic energy has units of joules. And work also has units of joules. So kinetic energy and work have the same units. So they're closely related. Now, I put this all over here. Kinetic energy is always positive. Okay? The reason kinetic energy is always positive, I'll put over here. Okay? This is always positive because mass is always positive, and speed's a real number, and when you square that, that's always positive. So by definition, kinetic energy is always positive, and it's a scalar. Okay, mass is a scalar, speed squared is a scalar. Okay, so we had, this is the last step I had right here. Okay, so the work is 1/2 mv final squared minus 1/2 mv initial squared. That's K final, that's K initial. So that says that the net work, okay, so the net work done by all the forces, remember I had a whole bunch of forces. Oh, I'm sorry, I had one force. Last problem, I had a whole bunch of forces. But you would add up, okay, actually in this problem, I didn't really draw mg and normal force because we already saw in the problem before that mg and normal force do no work. So normal force did no work, mg did no work. The only force that did work was that pushing force. And we saw that the net work done by that force results in the kinetic energy changing. So in chapter 7, this is called the work energy theorem. So the net work done by all external forces goes into changing the kinetic energy. So I just rewrote that down here from up here. Okay, now it's more intuitive if I take this expression, work energy theorem, and solve it for K final. So I brought K initial over. So this is another way of looking at Newton's first law when we start at forces. Okay, we could have said Newton's first law like this. We could have said, set of a body at rest remains at rest. We could have said, for a body with zero kinetic energy, the final kinetic energy will stay zero unless some force comes by and does work. Okay, or we could have said for Newton's first law, body moving at straight line at constant velocity will continue to do so. Or we could have said a body moving with constant kinetic energy will continue to move with constant kinetic energy unless some force comes by and does work to speed it up. So work energy theorem is just another way of looking at Newton's first law. So in the previous chapter, we would say, okay, you apply a force and the object accelerates. Now we say that force did work and the kinetic energy changes. And since kinetic energy has the speed in it, you could say, well, the force does work to speed it up, but we say the force does work, okay? And because of that force doing work, the object is going to acquire some kinetic energy. Okay, so we talked about energy being the capacity a body has to cause change, okay? And then I define work is energy being transferred to or from a body due to a force acting on it. So here's an example of a pendulum. Okay, so pendulum starts here. Whoops. And pendulum starts there. Okay. And let's say you lift the ball from B to A. So you did work to lift the ball from B to A because you applied a force to it. Okay. So because of the work done by you, the pendulum ball has acquired some form of energy. Okay. So you did work and then energy's been transferred to the ball. Now you let go of the ball at point A, and the ball's speed increases as it swings down from A to B because gravity is doing positive work. Okay? Remember, work is energy being transferred to or from. If it's being transferred to a body, the work done is plus. If it's being removed from a body, whoops, it'd be negative. Okay, so here it's going faster, so gravity's doing positive work. As it goes past B and goes up to C, the ball slows down. Okay, so we're going to see that the work done is negative because gravity is removing kinetic energy from the ball. So even though work is a scalar, it's defined in terms of two vectors, and thus, because of that dot product, sometimes the work can be plus, sometimes the work can be minus. So think of net work as change in kinetic energy. So work is positive if it helps to speed something up, okay? Meaning it would increase the kinetic energy. Work done by a force would be negative if it would tend to decrease kinetic energy, meaning acting against the direction it wants to go. Okay. All right, so I want to consider a system of objects. So the book will use this word system, okay? So let's say I'm holding a baseball, okay? Or let's say the baseball is just attached by a string, all right? Either way, the system is the ball and the earth, okay? Without the earth, I wouldn't have to fight gravity, all right? So that's what they talk about a system. So the ball is bound to the earth via gravity. So I'm going to slowly lift the ball from point A to point B. Okay, now what I mean by slowly is I start at point A at rest, and 2 weeks later, I wind up at B. That's how slowly I'm lifting it. So I'm not accelerating it quickly. I'm lifting it slowly. Okay, so I want to calculate the net work done by all the forces and see if it agrees with the work energy theorem. So it's the net work done by all the forces should equal the change in kinetic energy. Okay, so I look at the ball, and there's two forces that act on the ball, gravity and my hand pushing on it. So the work done by gravity, I know I wrote mg last time, but I'm just writing this the subscript g, this is the work done by gravity. So by definition, because it's a dot product, it's a constant force, so it's just the force times the distance h, okay, that I'm moving and going from A to B, I call that height h. So it's the force times the distance through which the ball moves times the cosine of the angle between those forces. So mg points down, but I'm moving upward. So the angle between mg and the direction it's moving is 180 degrees, and cosine of 180 is minus 1. Okay? The work done by you, there's your hand, okay? Okay, work done by you is the pushing force, you're pushing up, okay, times the distance to which the ball moves, times the cosine of the angle between those two forces. So in the picture, pushing force points up, it's moving up, so the angle between them is 0 degrees. Cosine of 0 is 1. But you're moving this slowly at constant speed, acceleration 0. And the acceleration 0, these two arrows are equal and opposite. So if the ball weighs a pound, you would have to push upward with a force of a pound to move it at constant speed. So that pushing force is just the weight of the ball. So pushing force is mg. Okay, so the work done by gravity is minus mgh, work done by you is plus mgh. And so when I add those two together, there's my minus, there's my plus. So the total work done by all the forces is 0. Okay, so that's consistent with the work energy theorem. Net work done was 0, so the kinetic energy can't change. Well, look at my picture. I start at rest, initial kinetic energy is 0. I wind up at rest. Final kinetic energy is 0. Okay, so that agrees. So that's consistent with the work energy theorem. Net work done by those two forces 0. Kinetic energy didn't change. Okay, but we keep saying that work is the transfer of energy. Okay, so you did work. Okay, that one force. Okay, you did work of mgh. So that must mean that the work done by you transferred some type of energy. Okay, so that work done by you, okay, didn't change the ball's kinetic energy. Started at rest, ended up at rest. Okay, so the work done by you, okay, you didn't change the ball's kinetic energy. Rather, that work done by you is now stored, keyword is stored, as a gravitational potential energy in the earth and ball system. Okay, so the gravitational potential energy is the energy a body has due to its position in a gravitational field. Okay, so the higher you are above the earth, okay, the bigger the gravitational potential energy with respect to the ground. Okay, think of it as taking something heavy like a brick. Okay, holding it just right above your foot. If you drop it, it's going to hurt your foot a little bit. If you raise the brick up 3 feet, okay, that brick now has a greater potential to hurt your feet. Okay, so the higher it is above your foot, has a greater potential energy. Okay, I want to add one more thing here. Most books use a capital U for potential energy. I think even in your chemistry book, they use a capital U for potential energy. Our book uses PE for potential energy, okay, which is fine, but why use two symbols when you can use one symbol, okay? For example, every book uses K for kinetic energy, okay? We wouldn't need to write KE for kinetic energy. One symbol's better, okay? But this book uses a PE, so I'm going to stick with this capital U for a little bit. So we're going to write capital U for now, but eventually when we start doing conservation of energy, I'll go with what the book is using, and I'll use PE for potential energy. Now here's a weird thing. Okay, what's the symbol for what's the symbol for potential energy? So almost every book on the planet uses a capital U for potential energy. Okay, so when we raise the ball up at point B, where's point B? There's point B. Started at A, lifted the ball all the way up to point B. Okay, so you did that much work to lift the ball up. Work done by you didn't change the kinetic energy because it's at rest at the top, but the work done by you is now stored as a potential energy. And that potential energy at B is called a potential energy, because that's a good word for it, because that energy is potentially available to be converted or transformed into other forms of energy. So if you drop the ball at point B, the ball would speed up, okay, and the kinetic energy would increase. So you did work to give the ball potential energy. If you drop it, that potential gets converted into kinetic. And essentially that's where we're headed, into the concept of conservation of kinetic energy. Okay, so the concepts aren't that difficult, but there's a lot of words and verbiage in this chapter. So you'll also maybe see in the chapter that potential energy is an energy due to configuration. Okay, it's a potential energy due to how a system is configured. So imagine you take a rubber band and you stretch it and you hold the rubber band. Okay, so you did work to stretch the rubber band. Okay, the work done by you is now stored as potential energy in the rubber band. You let it go and it snaps back into your other hand. Okay, we'll see that a spring, right? You squished the spring in the launcher, so you now configured that system. Work done by you to squish the spring is now stored as potential energy in the spring. A battery. So someone did work to set up a chemical potential energy, and you get that energy back when you hook it up into a circuit. Okay, and then first thing you do next semester in 196 is you look at static electricity, charges at rest. So these charges like to repel. So it's hard to get 4 plus charges together. So you have to do work to assemble those 4 charges because they want to repel apart. So if those 4 charges can be contained like that, that would be an electric potential energy. It's due to how that system is configured. Okay, now, the other minutia in the chapter is potential energy only has meaning with respect to some reference point. Okay, so for example, like elevation. Okay, in the lab room, I could ask, what's the height of our lab table? Well, someone might measure 3 feet. Okay, but if you look on a map, government map, they might tell you it's 303 feet because the map is giving it with respect to sea level. Okay, so only changes in potential energy have any meaning. So in the picture we had before, I just redrew it without all the other things in it. Here's point A, here's point B. All right, so we're going to pick our reference point to have the potential energy to be 0 where I started. So the potential energy is 0 joules at A, and up here where the ball stopped, the work done by you to lift it was mgh. So the work done by you is now stored as a potential energy. So potential energy at point B is mgh. So the change of potential energy, okay, potential energy went from 0 to mgh. So the change of potential energy is mgh. Okay, or we can just say potential energy of the ball at point B is mgh, and that only has meaning with respect to the floor, okay, not with respect to, let's say, sea level. Right? And then the book will remind you that it's really the potential energy of the earth and ball system, okay, because if you took the earth away and you let go of the ball wouldn't fall anywhere because there'd be no gravitational field. Okay, but usually we just ignore the Earth is there and just talk about the potential energy of the ball. Okay. Now, the ball is at point B. Now let's say you drop the ball. Okay. As the ball falls, there's only one force that acts on it, gravity. So I want to calculate the work done by gravity as the ball falls from point B to point A. Okay. So I did that up here. So work done by gravity is the force, so here's my picture, my downward force, times the distance h that it moves through, times the cosine of the angle between them. So mg points down and h points down. So the angle between them is 0 degrees, cosine of 0 is 1. So work done by gravity is positive. Remember, any force that points in the direction the object's moving, that force does positive work. Okay? So work done by gravity is positive. But the potential energy decreases. Okay? The change of potential energy is final minus initial. Final is 0. Initial was mgh. So the change of potential energy is minus mgh. Okay? So the change of potential energy is minus mgh, but mgh, okay, mgh is the work done by gravity. Okay? So, and I just rearranged this. I took the minus sign, put over here. So the work done by gravity is related to the change of potential energy via a minus sign. So think about this. When you drop the ball, okay, potential energy decreases. Okay, it's getting closer to the Earth, has less potential to hurt your foot the closer it gets to the Earth. So potential energy gets smaller, okay, but gravity is doing positive work to speed it up. So these two things are related with a minus sign. Okay? And whenever you have the work done by a force is equal to the change of potential energy, but there's a minus sign there, okay, that means that you have a conservative force. Okay, and we'll talk about what it means to have a conservative force. And we'll see that gravity is a conservative force. And the reason we spend time with conservative forces is because the word conservative has part of the word conservation. And we'll see that conservative forces lead to conservation principles. Okay. Now, what does it mean for a force to be conservative? So a force is said to be conservative if the work done by that force in moving a body from A to B is independent of the path taken from A to B. Okay, we're going to go to the next page. We're going to come back. So I want to see, what does that mean? Okay, so it's the same thing here. Oops. So a force is said to be conservative if the work done by that force in moving a body from point A to B is independent of the path. So here's a ball. Okay, so think of, you're looking at a ball maybe at eye level, and you want to raise it maybe a foot above you. You want to go from A to B. So I want to calculate the work done by gravity going from A to B. All right, so that's over here. Work done by gravity going from A to B. So as it goes from A to B, now again, it doesn't matter if my hand's lifting it or if I have a string attached to the ball. I'm looking at the work done by gravity, not my hand or not the string. So gravity is the conservative force. Okay, I could have even thrown the ball up from point A, okay, and the ball's just traveling upward from A to B. So the work done by gravity, okay, by definition of work is the force, okay, times the distance to which the ball moves, times the cosine of the angle between them. So mg points down, direction it's moving is upward, angle between those two vectors is 180 degrees, cosine of 180 is minus 1. Okay, so the work done by gravity is minus mgh. Now, I'm going to use a different path. So instead of going from A to B upward, I'm going to take this other path. I'm going to start from A, still wind up at B, but I'm going to go from A to C to D to E to B. Okay, so I'm going to go from A to B, taking a different path. So obviously my hand would have to be holding the ball going in that different path. And I just added some extra distances. Like I added that length L, I added that length L. So I'm going to calculate this. So the work done by gravity going from A to C to D to E to B is the work done by gravity going from A to C. Then I have to go from C to D, D to E, and then E to B. Okay, that's what I did here. Okay, so for the first leg, okay, from A to C, okay, that's this picture here. It's the force mg times the distance, L, times the cosine of the angle between them. Well, mg points down, L points to the right. So cosine of 90 is 0. From C to D, this is C to D, I have mg points down, okay, but the distance that I'm moving is h plus L. There's h plus L, and mg points down, and the direction that I'm moving is up. So the angle between mg and vector h plus L, that's the distance I'm moving, is 180. And cosine 180 is minus 1. Okay, as I go from E to D, I'm moving to the left. Whoops. I'm moving to the left. Gravity points down. Cosine of 90 is 0. Okay, and then my last leg going from E to B, mg points down, L points down, angle between that 0 degrees, cosine of 0 is 1. So the first term is 0, and here I have mg h plus L, but cosine of 180 is minus 1. So I have mg h with a minus, and I have mg L with a minus, because that cosine of 180 is negative. That whole term is 0, and this last term is mg plus L. So that one cancels with that one. And all I'm left with is minus mgh. So the work done by gravity going the short path from straight up from A to B is the same as the work done by gravity going that other path. It's the exact same. Okay, so this is the litmus test for a force to be conservative. Okay, so I went from A to B, and I found the work done was minus mgh. So if the work done by that force in moving a body from A to B is independent of the path taken from A to B, and that's what I found, I took a different path, the work done is the same, then that force is said to be conservative. And the reason the work done is the same is because gravity always points down. And when I'm going in any kind of zigzag path, okay, any path that goes horizontal, okay, there's going to be no work done along that path because mg points down, and the cosine, definition of work has a cosine, and all those horizontal motions, the work done by gravity in those horizontal motions will be 0. So it doesn't matter which path you take to go from A to B. Okay? Work done by gravity is the same. And that means that the state of the system, meaning the earthen ball, is the same. Okay, so how do I know that the ball has the same state of energy at point B for both paths? Well, if I take the ball and go on the first path, so I lift it from A to B, okay, so let's say potential energy is 0 here. I lifted it A, now the work done by me is stored as potential energy. I let it go, it falls to A. So the ball would have some speed, let's say if it hit my foot. Okay, or if I put a photo gate there, I can measure the speed. So that's potential energy B. When I drop it, it has kinetic energy. Now, if I took this other path, okay, this other path from A to C to D to E to B, okay, and I held the ball there at point B, okay, well, how do I know the potential energy is the same? How do I know the energy state is the same? When I drop it, it's going to have the exact same speed when it hits my feet because it started at point B with potential and it ended with the exact same kinetic energy. Okay, so since the work done by gravity was independent of the path going from A to B, there's some property of the ball and earth system that depends only on the initial and final positions of the ball. Okay, and that property or that concept is the idea of a potential energy. Okay, so it's independent of the path I took to go from A to B. It only depends on the initial final states, and that's going to be a huge advantage because I don't really care what path I took, but it only depends on my initial spot and my final spot. Okay, and another way to think of it is a force is said to be conservative if the work done by that force, again, think of gravity, the work done by that force can be stored as a potential energy and be fully recoverable. So that was point A, that was point B. So here's the ball. So I could lift it up to point B. Ball now has potential energy. I let it go, now it's kinetic. I lift it back up, has the same potential. I let it go, falls down, has the same kinetic. I lift it up, has potential. I drop it, has kinetic, and so on. Okay, so it's fully recoverable. And we'll see the exact same pretty soon with a spring. You squish the spring, then you let the spring go. You squish the spring, you let the spring go. Okay, you get all that work back as mechanical energy. Okay, so only conservative forces have potential energy functions. Okay, like a string, tension of a string. Okay, that doesn't have anything that's stored in it. We'll see that friction, get a little ahead, but for friction, if you slide something, kinetic friction points backwards. Okay, so you throw something, it slides. It ends up stopping. V final is 0. And all that energy is lost to heat. Okay, there isn't anything stored. You don't get that back. So only conservative forces have potential energy. And the conservative forces that we'll work with is gravity. Eventually we'll see springs. Okay, and the non-conservative forces will be kinetic friction and, for example, the string tension. Okay, so the advantage of having a conservative force, we'll see that eventually energy will be conserved. Start here with no energy, you do work, you get potential, you drop it, and you get kinetic. They can all be accountable for. Okay, now this thing here, okay, so if I read this, this thing says, this symbol is the net, okay, so that's the net work done by a conservative force, and this little circle here, okay, this little circle means a closed path. Okay, it can mean a closed path. So this says that the net work done by a conservative force along a closed path is 0. And if that's the case, then you have reason to believe you have a conservative function, conservative force. Okay, the closed path means we just did this. We went from A to C to D to E to B. Now I'm going to keep going and close that path. I'm going to go from A to A. So we already went from A to C to D to E to B. Now I'm going to go back to A. So the work done by gravity, okay, the net work done by gravity along that closed path is the part we just did, okay, from A to C to D to E to B, going back from B to A. So here's the one we just did on the previous page. That was from A to C to D to E to B. Now I'm going to go back. Now I'm going to go from B down to A. Okay, so in this picture, work done by gravity going from B to A is there's the force. I'm moving through a distance h, so gravity points down, the direction I'm going is down, angle between those two vectors is 0, cosine of 0 degrees is 1, so I'd get mgh plus, I get minus mgh plus mgh, so the net work done by gravity is 0. Okay, so that means if I start at A, okay, let's say potential energy is 0, and I wind up back at A. Okay, the net work done by gravity is 0. Okay, the state of the system hasn't changed. Now, if that was, let's say you're looking down at this is a block, and you're moving it on a rough surface. Okay, you wind up at the same point. Okay, system is not the same. You've generated heat with friction, so that's why friction would be a non-conservative